Hello, my name is Brian Roten, and today I will be presenting voltage regulators. Voltage regulators are also known as voltage controllers, and they are a group of electronic components that are designed to take a varying input voltage and produce a constant output voltage based on the desired circuit construction. There are two primary types of voltage regulators, one being linear voltage regulators, and the other being switching regulators. The primary difference between the two is that linear regulators have a much lower efficiency than switching regulators. For this presentation, I'll be focusing specifically on switching regulators, of which there are several different types, including step-up regulators that provide a higher output voltage than the input, step-down regulators that provide a lower output voltage, inverting regulators, which provide a output voltage that has the reverse polarity of the input, and step-up, step-down regulators, which produce either a higher or a lower output depending on the desired output. And to the right, I have an example of a buck-boost converter, or a step-up, step-down regulator, which is what I will be focusing on for the rest of this presentation. What they do specifically is switching regulators. They are designed to convert only DC voltages to other DC voltages, earning them the name DC to DC converters. Step-up, step-down regulators specifically are called buck-boost converters, and they specifically change the input to either a higher or a lower value depending on the desired output. Buck-boost converters operate using two distinct modes, one being the buck mode or the bucking mode, and the other being the boost or boosting mode. While in the buck mode, the converter will produce a lower output as compared to the input value, while in the boost mode, it will produce a higher output as compared to the input. Usually, the devices operate with several different components, including a switch, which is usually a transistor, a diode, which is used to control the current flow in the system, a inductor to control energy storage, and a capacitor to control energy dispersion and stability. The while the while the switch is in the on state, the energy is stored within the inductor and is dispersed by the capacitor while it's in the off state. The converter's output voltage is also controlled by its duty cycle, or the amount of time that the switch is open versus the amount of time that the switch is off or closed. While the switch is in the on position or the closed position, the input voltage is connected directly to the inductor, which will fill the inductor with capacitance with current until its maximum current value. And once the maximum current value is hit, the switch switches to the off or the open mode, in which the current and the inductor will be passed through to the load, which will increase or decrease its voltage based on the desired configuration. While the circuit is in a resting or a steady state, the inductor has absolutely no voltage across it whatsoever, so no current is exchanged. Here I have a couple equations for the switch power, the switch voltage, while it is in the positive or on position, the the voltage inside the switch is calculated by the power supply voltage multiplied by the time that it's on, and while it's negative or off, the switch voltage is calculated by the load voltage multiplied by the time that it's off. Buck-boost converters, they operate in two separate modes, each controlling a different current setting for the inductor. One being the continuous conduction mode, or CCM, in which the current inside the inductor never truly reaches zero and is always positive at the output. Some advantages to this mode are the circuit overall is better responsively, and it has a higher efficiency. Some disadvantages, or one disadvantage, is that the inductor values of the circuit need to be higher to facilitate the heavy current requirement. The other mode is discontinuous conduction mode, or DCM, which means the current inside the inductor will periodically reach zero. And some advantages to this mode are smaller inductor values are needed, and the current of the circuit can be smaller or more compact. Some disadvantages is that the output voltage is less efficient, and it has a higher ripple, meaning it's not as stable. And some buck boost converters also operate in both modes, depending on the situation. They can change between one or the other as needed. Continuous mode, or CCM, is frequently used in large power applications, as well as applications in which the output voltage needs to remain relatively constant or has a very low ripple. This is due to its highly reliable and efficient output and how responsive the system is. DCM is typically used in low power applications in situations where the load current, the current in the load, is extremely low, due to the fact that it has such a low efficiency and the output voltage is unstable and has a high ripple. When designing buck boost converters, you have to consider a couple factors, including the selection of the components you're using, the strategy by which you're going to control said components on or in the system, the calculations required for the parameters of the converter, and the capacitances of the capacitors to provide steady output. When considering components for the converters, you want to make sure that your switches are rated high enough to be able to handle the appropriate, or they're rated appropriately to handle the required voltage and input values, or voltage and current values, sorry. And that the diodes have low enough forward voltage drop, and quick enough recovery time to limit the amount of the efficiency loss from the switching from on and off mode. You also want to make sure that your inductor values are high enough to be able to maintain the conduction mode that you choose. Capacitors for the circuit need to be chosen so that they have low enough series resistance and high enough capacitance to provide a stable and steady output to the load. When considering the control strategy, you want to consider that the output voltage is usually managed with pulse width modulation, which is used to change the duty cycle of the switch, and is therefore used to increase or decrease the output voltage. You also want to consider the stability of the output, and pick a strategy in which the steadiest output is acquired. When considering the parameter calculations, you need to consider the duty cycle, which is going to control the output voltage, and the inductance, which will determine your conductance mode, as well as the overall ripple of your output voltage. Buck boost converters typically have several essential components, including a switch or switching device, which is usually a transistor, which is typically a MOSFET or a BJT. And these are chosen to regulate or control the inductor's current flow, and to determine which mode the converter is going to be operated in, as well as the overall output voltage. The diode is chosen to help direct the current from the inductor to the load, and to prevent the capacitor from outputting backwards towards the input voltage rather than forwards towards the load, while the inductor is chosen to store energy and disperse it to the capacitor, which then disperses it to the load depending on the switch's on-off cycle. And the capacitor is chosen to provide a smooth and steady output to the load. Finally, there are a couple extra components, which are input and output filters that help reduce the interference and noise from outside sources, which help provide a more steady and stable output. And here I have listed a couple equations for the parameters. The duty cycle will be equal to whatever the output voltage, the desired output voltage is, divided by the input voltage added with the output voltage. The output voltage is as a function of the input voltage, which is the input voltage multiplied by the time the switch is on divided by the time the switch is off. To find the inductor value you need to multiply the input voltage multiplied by the duty cycle and divide that number by the amount, the current in the change in the inductor's current over the amount of time that it changes, and multiply that value by the frequency by which your switch operates. There are, however, a couple considerations that have to deal with the efficiency and the overall losses of the circuit. Some of the factors affecting these are losses in the circuit conduction, the efficiency of the switch operation, losses due to magnetic energy, and the losses based on the circuit control. A couple causes of circuit conduction losses are individual components having high natural resistance values, the current that flows through the switch while it's on, and the amount of resistance it also has while it's on. The off resistance, since it's an open circuit, doesn't really affect the circuit overall. And then the last cause is the current through the diode and the forward voltage drop. The switching efficiency is affected by the time that the switch takes to turn from on to off, and also vice versa. Essentially, meaning the frequency by which the switch switches from on to off will overall affect the efficiency of the circuit. A couple causes for magnetic energy loss would be the core material you choose for your inductor, as well as the method that you use to wind your wire around your inductor. Both of which can be improved by picking an improved method of winding the wire around the inductor, and picking a more stable core material for the inductor. As for the wiring and the control of the circuit, it doesn't really it doesn't have an intense effect on the loss of efficiency for the circuit, but you still need to consider it when you're considering the loss of the overall efficiency of the circuit. A couple advantages of buck-boost converters are that they are extremely energy efficient. They have very few external components. The components used inside the circuit itself are considerably smaller than the other converters. The biggest advantage being that you can either step up or step down your output voltage depending on your situation, and they're also not cheap, but they are they're very efficient in the cost department. A couple disadvantages is that you can't really get high gains out of them due to the fact that the duty cycles can't get low enough to produce an extremely high gain value, and the output and input values aren't necessarily isolated from one another, which could cause some short circuit issues. And in this figure, I have an example of a buck boost converter that you can see has the capacitors, the inductor, and it also displays the output voltage as well as the output current. Some uses for buck boost converters are portable and handheld devices, or such as your cell phones and laptops, which they can help to regulate the battery percentage inside the battery drop inside the device to ensure that batteries will last long enough even when they drop below the minimum required values. They also help in energy collection and storage systems by regulating the amount of input that is input to the system at once. They can help with vehicles, which also specifically electric vehicles, inside the chargers and the charging capabilities to regulate and either increase or decrease the input voltages to ensure the vehicles don't overload. They're also used inside industrial and communication technologies. And finally, they're used in lighting systems, specifically LED lightings, to help power the individual bulbs and regulate the amount of current and voltage that's flowing through said bulbs. And to the right here, I have another figure, but this one is of a electric vehicle that uses a power converter to help regulate the discharge of its batteries. Within my Capstone project, I used specifically a boost converter that would increase the voltage from the batteries for my system, depending on how low. That would increase the battery's voltage for no matter how within a voltage range input to determine how to help regulate the input voltage to my system, and ensure it didn't go below the required value. And listed here, I have a couple of my references or a list of my references for this presentation. Thank you all, and that's all.